All right, let's talk about the forces involved in rolling and kinetic energy. Let's talk about the kinetic energy first. We know that when we have a mass moving with some speed or some velocity, that the kinetic energy, no matter what it is, okay, you'll see this for the rest of your life, or for the rest of your academic career if you're looking at the motion of a particle. Its kinetic energy will always be 1/2 mv squared. This is a scalar, not a vector, right? We also learned that something that is rotating, so use something that's obvious to rotate like this. This is maybe the center of mass, has some even mass distribution about it. Well, if this thing is rotating, it's going to have some other kinetic energy associated with just the rotation. So we have some for translation, and we have some for rotation. And it's going to be at 1/2 I omega squared. So the I would be your moment of inertia. That depends, remember, upon the distribution of mass, or the shape of the object and the mass of the object. And it also depends about what your axes you're rotating it about. So remember, if I rotated this about here, it's actually easier than if I rotated it about here. We have a different I for each of those cases, or anywhere in between. And we have a different I for every kind of shape that exists, right? Hollow cylinder, solid cylinder, anything you can think of, right? Cone. If we want to rotate this, we can figure out what the moment of inertia is. We could rotate it about this if we wanted to, but we'd have to find the I. It'd be a little bit more. So basically, we say the kinetic energy of something that is, we'll call it rolling, right? General plane motion, but right now, let's keep it simple, call it rolling, is going to be the combination of both of those. The kinetic energy from the translation and the kinetic energy from the rotation. So you can see just by a mass spinning or rotating as it's traveling through the air, like a projectile or something, just the fact that it's rotating, it now has more energy. Okay. Now, let's say we talked about we could find, we had a wheel. If it went through some angular displacement theta, we could figure out what this arc length was, or the distance it traveled. That arc length, by the way, is equal to however far it traveled on the ground, right? Is equal to r theta. We found that the velocity of some point, so the velocity of the center mass, if this is the radius, is equal to r omega. So, which makes sense. We take another time derivative. We get the acceleration of the center of mass to be equal to alpha. These are both actually cross product terms. Once again, take dynamics with me. We'll get into this further. But to simplify, we'll just keep it as we can get the direction from the picture, basically, if we had to turn it into it. But there's 3 relationships relating the linear motion to the rotational motion. In these rolling problems, you may encounter friction. So if something is rotating in this direction, there's reaction stuff going on here, but say the force is in that direction, which would cause an acceleration in this direction of the center of mass. Don't assume that it doesn't slide. Don't assume it's always static friction. So you could have kinetic friction. It could actually translate for a little bit before it starts rolling, right? See a pool ball do that. It'll move without spinning, and then the friction acting on the ball, slowing it down, is what causes this to start faster and faster. And we're going to talk about the friction and what's causing the rolling by looking at an incline plane. So let's make one. Let's say we have an incline plane right there, and this is some angle theta, and let's put a rolling object on it. Something like that. The center of mass of this object is going to be right at the center of the sphere, or the hoop, or the wheel, whatever this is. Let's take a look at the forces. This thing's going to roll down, right? We've looked at blocks before that just slid down. That was just translational motion. That had no rotation at all. It could have had a frictional force, right? But now the friction is going to be what's causing this thing to rotate. So let's do a free body diagram. We have the force due to gravity, mg, right here. If we break that up into components, I would have a perpendicular component and a parallel component. Where, this would be Fg cosine theta, right? Because this becomes our angle theta. And that gives us the normal force acting perpendicular to that plane. And what we need to look at is that we could have some frictional force. If there's no friction, it's just going to slide down without rotating, right? So imagine there's some friction, F of S right here, pointing backwards. And that and the contact point right here, as well as this component, if we move this up here, that's F sine theta, right? Those two components are going to, those two forces are going to dictate how fast this rolls and moves down the ramp. What's happening here? Well, we have a torque. There's some distance that this is acting, right? Some distance that the force is acting perpendicular to, and that's causing this thing to rotate. It's rotating about this point of contact between the plane and the object. And we can actually get a formula for stuff like this. You should really just apply Newton's second law for linear motion and Newton's second law for rotations. So we'll call it for translations and Newton's second law for rotations. Okay, so what do we get? Keep the picture up. Well, we found out before that really only the components in the direction of the plane are going to give us information about the motion. We need the perpendicular components to figure out the frictional force. But what do we get? We have some frictional force acting up the plane. Then we have the mass times m. This is mg sine theta and mg. There we go. We have mg sine theta going down the plane. And that's all going to equal the mass times the acceleration of the center of mass. So, find another color. There's going to be some acceleration of the center of mass. And there's also going to be some rotation alpha, angular acceleration. So we'll be able to relate those two with the acceleration of the center of mass is equal to r alpha. This will be one equation we need. This is two equations we need. Let's do Newton's second law for rotations now. Newton's second law for rotation says that the summation of the torques is equal to I alpha, the moment of inertia times the angular acceleration. Remember, this is the summation of the forces is equal to mass times acceleration. This is the analog for rotations. What would cause the rotation about this point right here, the point at the center? The component right here of force going down the incline, since it's concurrent through that point, doesn't cause a rotation, right? If I have a rod with a center of mass right at the center, if I push right at the center, the whole thing's just going to translate up. If I push out from the center, it is going to rotate and translate up. So this frictional force is actually causing a torque for us. And so what we get is that the frictional force times the distance it's acting d. Let's call it, I don't know why I called it d. Let's call it r. Is going to equal to whatever object we have, I for the center of mass, times alpha. And we'll call that equation number 3. So if we put 1, 2, and 3 together, we can get a description for the acceleration of the center of mass. What we get, it's going to be going left down the incline, is the minus sign, g sine theta over 1 plus whatever object we have. So this could be anything, right? I, the moment of inertia for anything. And this is divided by mr squared. And so once again, you'll also need the relationship that the acceleration of the center of mass is equal to r alpha. So putting those three together gives us an equation we can use for something rolling down an incline. Okay, I'm going to go ahead and knock out one more topic, and this covers sections 11.3. And this is the yo-yo. I was going to assign this to you, but I know y'all are tired. If you don't know what a yo-yo is, it's a thing you put on your finger, and it has some, let's make a better circle than that. It has some outer radius and some inner radius. Pretend those are circles. And your finger is attached to a string that goes to the one that winds up, so that it spools up around here. And so we can say that this is some r naught, and then the full outer radius is some r. Okay, what we're interested in is the fact that we have a tension going up here. And what other forces do we have? Is anything touching it? Well, that's the tension. Is gravity acting on it? Yes, it is. We have mg going down. Notice in this problem, they'll probably give you that outer radius right here, r, but that's used for calculating the moment of inertia? I. The inner radius is the one which is actually providing the torque, right? We have a force right here acting at some perpendicular distance, so there's a torque. That torque is going to be equal to that tension times R naught. And if we look at this just like the inclined plane problem we just did, except we bring this angle theta from whatever it was not equal to perpendicular or flat, right? That's the definition. The inclined plane was theta equal to somewhere in between 0 or less than or equal to, or not equal, just less than 90. But, dang it. Greater than 0, but less than 90, right? Or that theta was greater than 0, but less than pi over 2. Either way. What if we take this all the way to 90 or pi over 2? So we're going to let this angle go all the way up and make it vertical. In that case, we can apply Newton's second law for rotations plus Newton's second law for the translational motion, because this whole thing goes down, right? The whole point of the yo-yo is the whole thing moves down as it unwinds. And we can basically use the same formula that we had right here for the inclined plane. The only difference is that before we had sine theta in our answer. Well, the sine of 90 is 1. So our new solution for the acceleration of the center of mass is it's going down, so a minus. We just have the g term. There's the sine of 90 right here goes to 1. And this is all divided by 1 plus the moment of inertia for the center of mass, all divided by mr squared. And that's r as the inner radius. That's the one where the torque is being applied. It's not being applied out to the outer edge. So once again, they gave you these 2 dimensions for where the string winds up to, and they also gave you the radius of the edge. That outer radius would be to calculate the moment of inertia. Alright, we'll look at torque a little bit deeper next time.